So, given a rectangular or Cartesian equation, we want to create a corresponding set of parametric equations. And by the way, the way to parameterize a rectangular equation is not unique. In fact, there are infinitely many ways to get this done. For now, we're going to do a few in which it doesn't matter which one is it. However, let me give you an idea here. For, in this case, the simplest case, or the simplest way, give t to the independent variable. So give t to the independent variable. That's usually the easiest way. Well, of course, there's other ways, and we're going to learn a new way to parameterize equations of lines. So we're going to do, well, you'll see later how we're going to parameterize a line using this traditional method, and then we're going to learn a new method to parameterize equations of lines. Well, example number 6. Write a set of parametric equations for the rectangular equation y equals 2 over x minus 1. All right. So actually, I'm not going to do only one version. I'm going to do a few versions. You'll see. So number 1, going the most natural way, the simplest way, give t to the independent variable. And then in this case, the independent variable of y equals 2 over x minus 1, that's the variable x. So in this case, your x will have the letter t. What? Why? Well, the result of substituting t wherever you see the letter x, which in this case is 2 over x minus 1. And that's it. That's all we do. That's one way to parameterize an equation. Yes? That's what I meant, but not what I wrote. Thank you. Yeah. So that's a t. Another example. How about t minus 1? Because, t plus 1, because why not? Because we can.
Then y.
Y equals to 2 over t plus 1 minus 1, which is 2 over t. And that's another possibility. How about another possibility? I don't know, x equals e to the t, because we can. 2 over e to the t minus 1. How about x equals, let's think of something else. Natural log of t, or x equals, let me do the square root of t. Y equals 2 over root of t minus 1. And just like you just said, x equals ln of t. Y equals 2 over ln of t minus 1. Well, what can we do with all these different ways to parameterize the same function y equals 2 over x minus 1? Well, we'll see a lot about this when we look at the very last example. In the meantime, let's just do all this and just write some of them, and that's it. Write a set of parametric equations for the vertical line x equals to 4. All right, let's draw the vertical line. X equals to 4. 1, 2, 3, 4. And that's our vertical line. X equals to 4, not y equals to 4. X equals to 4. And while in this case, even though this might look a little weird, a little tricky, we already have a freebie here. They're telling us that x equals to 4, all right? And when we write the set of parametric equations, x equals to 4, y equals to, I'm going to say anything. I'm just going to say t. Because it doesn't matter the value you plug in for t. For example, x will always be 4. However, plug in y equals to say 0. That's going to give us the order pair 4 comma 0. Is that order pair on the vertical line? X equals to 0. What if I say t equals to 75? Is the point 4 comma 75 on the graph of x equals to 4? What about for t equals 50 million? It's going to be there, We can design it in a different way as well. X equals 4. How about y equals to, I'm going to say t cubed. T cubed is going to output this same line as well. However, well, I don't want to talk about the differences for now until we look at the very last example that you'll see. So this is another way, this is one way, this is another way. I don't know, maybe a weird polynomial if you want, maybe a trigonometric function perhaps, or no, maybe not. Maybe not a trig function. Well, the trig function will have different certain limitations, so we may not want that. So this is how we parameterize a vertical line. Now that we have the vertical line, let's look at another line. That is, in this case, write a set of parametric equations for the line that passes through 1, 5 and 3, 2. And well, what we're going to do for this example and the next one is going to prepare you guys for Calc 3 next semester, for those of you who are going to take it, because more often than not, or pretty much a vast majority of the semester, you will be parameterizing equations, because you will look at this new type of functions called vector valued functions, in which in this case you're going to have like a path, maybe a curve or just a straight line in 3 dimensions. And in that situation, as opposed to what we work in 2 dimensions, we have the slope rise over run. However, in 3 dimensions, we don't have a rise over run thing. Actually, we have, for example, from the origin, we have a line pointing in the direction of one vector or another vector, etc., which is going to be something else. Yes, there will be some similarities on how those values will be computed, but well, you'll see the next example. In the meantime, so we have a couple of points. Let's parameterize this using the traditional way. The traditional way, well, find the slope. 3 minus 5 over 2 minus 1. That is the difference of the y's over the difference of the x's. That's going to give us negative 3/2, right? And well, we have the slope. We can use the slope in any of the points. I'm going to use the first point, y minus. That's what wait, no, because it's supposed to be 2 minus 5 and 3 minus 1, right? Yes, I don't know what happened here, all right? So, yeah, and it's still 3/2. So I was looking anyway. Y minus y1 equals m times x minus x1. Well, I'm going to use the first point as a reference. Y minus 5 equals negative 3/2 x minus x1, which is 5. And I'm going to distribute this. Okay, number 1, y minus 5 equals to negative 3/2 x. Negative times a negative is positive. 3 times 5, that's a 15 halves. And subtract 5. Oh, come on. Yeah. So again, that never happened, right? Yeah. Oh, it's on video anyway. It's on tape anyway. So, damn. Okay. So add 5 to both sides, and y equals to negative 3/2 x. 3/2 plus 5, 13 halves. So that's the equation of the line containing those 2 points. Let's parameterize it the traditional way. That is, letting x to be the parameter t and y equals to negative 3/2 of t plus 13 halves. All right, just that. However, that's a little time consuming, you know, having to find the slope and then having to go back to the point slope form of the line to obtain the line and then do the traditional way to parameterize by just letting t the independent variable. It's fine. It's a valid parameterization. Again, parameterizations are not unique. There's infinitely many ways to parameterize a rectangular equation. However, the general form of a line through 2 points is going to be given in this form, in which essentially this is, you know, x2 minus x1, that's the delta x times t, plus x sub 1, and delta y sub t, plus y1, which in this case is the change in the x's times t plus the initial value of the first point, the x on the initial value, that is x1, and the same in the y direction. Well, what is that x2 minus x1? For those of you who may have seen vectors already, I mean, you're not supposed to know this, you're not expected to know this, but essentially, well, this actually is going to make a lot more sense when you get to the vector notation in Calc 3. So to find a vector that contains 2 points, all we do is subtract the final point from the initial point, the values of those points rather. That's going to give us a vector. And well, this line is going to contain that difference of those values in the x direction, the y direction, and well, you will get to the z direction in this case, because you're going to work in 3 dimensions when you get there, all right? So right now, don't even think of vectors because, well, that's not part of our objectives. Just use this formula, and if you don't apply it this semester, at least you already have this for next semester, which I'm pretty sure is going to be a lot useful. All right, and okay, so let's write a set of parametric equations for the line that passes through -8, 1, and 10, -5. But in this case, not the traditional way that we did before, but actually using this general form to parameterize a line. All right, so let's write the equations. X equals to x2 minus x1 times t plus x1. Y equals y2 minus y1 t plus y1. And well, x and y are going to be, number 1, the difference in the x's, that is 10 minus -8. Careful with the signs. T plus x1, in this case the x1 is -8. And for the y equation, that's -5. That's a -5 minus 1 times t, and plus the initial y, which in this case is 1. Just simplify this to get x equals 18 t minus 8 and y equals to -6 t plus 1. And that's another parameterization for a line. And in this case, well, notice all the variables t's are raised to the first power. Of course, that should be describing a linear equation, but in this case in parametric form. This is a lot easier, and this is what you're going to be doing next semester in Calculus 3. All right? Now, there's other situations in which you may need to satisfy a condition given a rectangular function with respect to its parametric version. Well, and that's our next example. Example number 10. Find a set of parametric equations that satisfies the given condition. That is, the function y equals x squared plus 3. And the condition that we need to satisfy is that whenever t equals to 2, then the particle traveling along that path has to be at the point 1, 4 whenever t equals to 2. So here is where we will play a little bit to be designers of parametric equations, designers of paths, or because check this out. Let's parameterize this the traditional way. That is, give the letter t to the independent variable. So x equals to t, y equals to t squared plus 3. All right? So let's test. Let's check if the condition is satisfied. That is, that whenever t equals to 2, we get to 0.1 comma 4. So when t equals to 4, do we get x equals to, oh wait, no, whenever t equals to 2, so that's going to be the 0.2, y equals to 2 squared, which is 4 plus 3, which is 7. No, we're not getting the 0.1 comma 4, right? So we need to make a change in the original set of parametric equations. And guys, don't erase this. Actually, just cross it so you can see why is this not working for our purpose. So raise your hand.
I was just thinking, like, to get the first point x equals, shouldn't we just do x equals t divided by 2?
T divided by 2. Whoa. You know what? I actually had a different version. I wasn't thinking of dividing it by 2, and actually one of the students in my other section came up with the same example, and it actually is going to work. So, and let me write it down. So, I'm going to write both versions, the one I had in mind and the one that you are sharing with us. So, number 1, x equals 2. So you said t over 2. And y rather, equals t over 2, quantity squared, plus 3. Let's see what happens whenever t equals to 2. So number 1, x and y. So 2 over 2, yes, that's 1. And 2 over 2, which is 1, quantity squared, that's 1, plus 3, 1 comma 4. All right? Let me give you the other version I had in mind. The other version is, well, another way to get x equals 1 when plugging in t equals to 2. How about t minus 1? All right. And from here, y equals to t minus 1, quantity squared, plus 3. Plug in t equals to 2. Check the magic. 2 minus 1 is 1. 2 minus 1, which is 1, quantity squared, that's also 1, plus 3 equals to 4. And either of these two sets of parametric equations actually satisfy the condition that whenever t equals to 2, that is after 2 seconds or after 2 hours, after 2 centuries, whatever application it is, the particle is at the point 1 comma 4. Sounds good?
Yep.
All right. Let's wrap up this section looking at one more example. Okay, this one example, okay, each of the following set of parametric equations gives the position of a moving particle at a time t. Well, notice we're talking about position. So, in a very similar way that in Calc 1 you took the derivative of a function to get the velocity, the second derivative to get the acceleration. Well, that's something we're going to learn next time. The calculus of this parametric equation. So in the meantime, let's see what's going on here. So we have 4 different sets, 1, 2, 3, 4. Each set gives the same function when we eliminate the parameter. However, there's going to be huge differences here. What are those differences? Well, number 1, let's start by plotting them. And no, I'm not going to make a table of values for every single one. That's going to take the whole weekend here. So, and well, I'm going to go to my graphing calculator first. And okay, so second, quit. Make sure that you are in radian mode and in parametric mode, for those of you who are using the TI calculator. And whenever you do that, that's going to give us again 2 equations, one for x and one for y. I'm going to type the equation, what is it, t to the 3rd power and t. Okay? So, and I'm going to plot, but I'm going to graph, but make sure when you're graphing these equations not to blink. Because if you blink, you may miss the direction in which the graph is being drawn, maybe from left to right or from right to left. So don't blink. Okay. How did it go? From left to right. And it went kind of quick, right? How do we slow this down? How do we turn it into slow motion? Well, go to the T step and make it a smaller number. I'm gonna go 0.01. That 0.01, it's actually plotting more points on a scale of 0.001 each. So that sure is gonna take longer to plot. What? I don't know. Window. What the hell, huh? This step is not accepting 0.01. Okay, let me go. Okay, let me go 0.1, see what happens. Okay, I wasn't even able to see the direction. Window 0.001. What the hell? Okay, let me second quit. Y, I'm gonna do, or rather, window. How about 0.005? Hopefully that works. Something bigger. Oh, okay, much better, right? It's slower, and we're able to see the direction and all that. So I'm gonna go back to the notes. So that's the graph of f of x equals, well, we don't know yet. However, again, make sure to draw arrows to denote the direction of the particle. Now, let's eliminate the parameter to find out what function is this. Okay, and again, that's going to take us back to what we learned last time. In order to eliminate the parameter, go to the easiest equation that you see in your set of parametric equations, and I think the easiest one is the second one. Solve for t. Well, it's already solved for t. All I have to do is write y equals to t, and x equals to t cubed, and all I'm going to do is replace t with y. X equals to y cubed, and to get y by itself, to get rid of the cubic, get the cube root. So y equals the cube root of x. And in fact, well, that graph indeed resembles that of a cube root of x. And well, it's important to state its domain, negative infinity to positive infinity. Well, that's clear from the graph. That's clear from the graphing calculator. We got both tails of the graph, all right? The positive, the one that points towards the east, and the one that points towards the west, all right? Well, we're going to talk about some sense of direction this time, because you'll see what's going to happen with the next example. So let me label this as part A, part B, and let's draw the graph. Part B essentially looks the same, however, that one has negative signs in front of each equation. Let's see what's the effect of getting those negatives in front of it. Okay, so I'm going to do a second insert negative, second insert negative, and I'm going to plot this graph. I'm going to click graph. It goes the other way. It comes from east to west this time. We need to, well, I'm gonna draw it in that direction. However, how do I gonna know later that I drew this graph from right to left? I mean, you saw it live, but we need to make sure that it goes like this, using arrows here. And well, let's do the same. Let's eliminate the parameter. And well, so the easiest equation, which is y equals to negative t, solve for t, that is negative y, and x equals to negative t cubed, which is really the same as saying negative quantity cubed. But what's this t? Isn't it negative y? Now careful when simplifying this, because what do we have? Inside of the parentheses there's a negative that is raised to the third power. A negative raised to an odd power remains negative, and times the negative that we have in front outside, that becomes a positive. And well, take the cube root, y equals cube root of x. And the domain, it's still the same. Negative infinity to positive infinity. Yes, even though it's going in the reverse direction, we don't say from positive infinity to negative infinity. No, interval notations and set notations, whether you use either one or both, we still express those intervals from the smaller to the larger, regardless of the direction dictated by the parameterization. Okay, so don't reverse this order; they remain the same. Let's look at the next example, letter C. And letter C, it looks a little weird. It looks a little weird, but okay, we'll find out what is that doing. So let's go to the graphing calculator and plot that. So number one, can we clear and clear? So that's a t raised to the 3/2 for the x equation, and we also have the square root of t seconds squared t. Okay, so again, don't blink, make sure not to blink. Well, yeah, I set it up to go slow motion. How is that graph different from the one we had before? We only have half of the graph, all right? Why is this? Any ideas of why this could be? Hmm? The 3/2 is fine, I guess. It's not about the 3/2. I think it's something else. It's the square root. The square root. All right. So if we go back to the parametric equations, y equals the square root of t is like saying y square root of x, right? Parameterizing the traditional way. However, think of the function y equals the square root of x, the square root or the square root of t, whatever dummy variable here. It has a restricted domain. Its domain is not the set of all real numbers. It's only 0 and larger than 0 and 0 to infinity. Well, and that's reflected on this graph right here. That's why we're seeing only the positive tail, in this case, the rightmost tail. Now, and let me be clear about something. So, actually, yes. I'm going to draw a solid bubble here for a reason. Okay? So, and in this case, draw the arrows in the direction that we got from the graphing calculator as well, right? And again, you could verify all this by plugging in different values of t for the different equations, for the two equations, and get different order pairs. All right, let's eliminate the parameters, see what we get. So the easiest equation of these two, well, I'm going to think of the square root of t instead of the t to the 3/2, because see, a rational exponent is a little more complicated than a radical, and in this case I'm going to call y equals to square root of t our initiation to eliminate the parameter. I'm going to square both sides to get t by itself. That's y squared. Writing back the equation for x equals to t to the 3/2. X equals to well, you know what? I think oh, no, never mind. So that's something to the 3/2, and that something, which is t, is y squared. Well, power of another power. We multiply the powers. When we multiply 3/2 times 2, these 2's cancel. These 2's cancel, and we're left with x equals to y cubed, which is y equal to the cube root of x. Isn't it the same function being parameterized in a different way? Yes, we get yes. Yeah, that's when we have even power, even indices in this case. So in this case, the domain, it's going to be not all real numbers like in cases A and B, but in this case, from 0 to infinity, and in this case, including the 0. What is that? All positive and 0. Yes, because the domain of the square root function, it also includes the 0. And we have one more. X equals to e to the negative 3t and y equals e to the negative et. That doesn't even look any close to anything that we had before, and that doesn't even look that this is parameterizing the cube root of x. But trust me, it is. Number one, let's parameterize. Or rather, let's graph the parametric equations, and in this case, e to the negative 3t and e to the negative t. Okay, let's graph. And again, don't blink.
The same graph.
It's almost the same. Here is where we need to discuss the usage of graphing calculators. All right. Well, let me draw the graph. First of all. And again, it looks similar. I mean, it's only half of the curve. Well, not yet. I'm not going to draw it yet. Let me take this back. Number one. So, for the previous example, the reason why we got only the rightmost tail of the function, that's because of the domain, or the restrictions of the square root of t, which in this case includes t equals to 0. Now the question is y equal to negative t ever equal to 0? So, for example, try to solve e to the negative t equals to 0. Take a ln to both sides. Undefined. It's negative infinity when we're finding the limit, but when we evaluate the function is undefined. And that's the main difference between evaluating a function. So evaluating a function is, can you step at that point? Yes or no? Is it defined? Yes or no? While finding the limit is, how close can I get? Doing small steps, and where is it that we're approaching to? Well, so for this reason, because the exponential function is never 0, it's not going to include the origin in its graph. In this case, that's why I made a distinction here, and I made it a solid bubble versus an open bubble over here. And just make a sense of direction. So, guys, here is my advice when it comes to using graphing calculators. Yes, they're very smart devices. However, they're not that smart because, number one, graphing calculators are not going to show you this removable discontinuity that we usually call holes, and it's not going to show you any vertical asymptotes or horizontal asymptotes. In this case, we need to have that in mind. We need to have in mind all our knowledge of asymptotes and discontinuities, in particular the hole discontinuities, because check this out. Do you see the hole in the origin in the graphing calculator? It's not there. Here is where we use our knowledge of how these transcendental functions behave. And in particular, it's the fact that e to the t is never ever 0. Now let's eliminate the parameters. So let's go back from exponential functions back to this radical function. I know it's kind of weird, but that's actually the thing, So let me make some space here. Alright, so there's a couple of ways to eliminate the parameter. And again, the easiest of the equations is going to be the second one because it's the one that doesn't have too many coefficients. One way to go about it is solve for t over here. That'll take a couple of steps. Number one, take a ln to both sides to eliminate the exponential and then divide both sides by -1 to get t by itself. That's a few steps. However, I'm going to do it in a different way. And the other way I'm going to go is, well, number one, y equals simply e to the negative t. X equals e to the negative 3t, which is the same as saying, well, Think of the result that we have on the exponent e to the negative 3t. This is a multiplication. You know, this is a product. That's the result of performing a multiplication, you know, like e to the negative t raised to the third power, power of another power. Isn't it the product of the powers? Well, y equals e to the negative t, replace it here. And x equals to y cubed, which is y cubed, and y. And it's the same function, isn't it? However, it's restricted. Its domain, based on this parameterization, it's not the same anymore. It's not all real numbers. It's not all real numbers. It's not from 0 to 1 to infinity, inclusive for 0. In this case, the domain is 0 to infinity still, however, exclusive for 0. That's the difference. Parentheses for 0, brackets for 0 in the previous case. Because in one case, the origin is included. In the second case, the origin is not included. Well, why do we care about all these ways to parameterize any function in general? You know, so you might want to use these parametric equations to design maybe the path of a rocket, you know, to hit, you know, a certain target, right? And it doesn't have to be, you know, in the military. You can apply this, for example, in the video game industry. You know, when you're designing mechanics for different games, for different weapons, you know, that you use, you know, you want to make sure that when you launch a rocket, it gets as far as this point. If you want to design another weapon, you know, to make sure that that the rocket goes forever in a certain direction or the other direction, well, then you would parameterize it. I mean, via programming, you would set this parametric equation to have an animation to do certain path, right? So different ways to parameterize rectangular functions for different purposes.